What we're looking at today, guys, is we're starting solving. Today will be the first day in several days of solving. And really that's what we're going to finish this chapter out with, is solving quadratics. Now there's lots of different ways that we can go about solving quadratics. And the first one that we're going to look at is solving quadratic equations by graphing. And then we're going to look at solving equations algebraically. And we may or may not get to some of the real life problems. If you're wondering where we're going to encounter a quadratic in real life, there's actually a good number of places. Because what is a quadratic? It's a U-shaped function, yes? Either stretched out or shrunk down. Well, is there anything in football that looks like a U-shape? Because if we think about when the quarterback throws the ball, because it goes up and then it comes down, it is actually a quadratic. Because really anything that is thrown in any way, shape, or form can be represented by a quadratic function. So that means realistically for golf, if they drive the ball or hit the ball, that is a quadratic function. We can represent it by a quadratic function. Anything that is falling, that has a starting point and then ending point, can be represented by a quadratic function. So parachute jumping, so jumping out of a plane, skydiving, not parachute jumping, skydiving, we can actually represent it by a quadratic function. Because even though it doesn't represent the whole function, an entire U-shape, we can represent where they start the jump as the vertex and map a kind of time over distance comparison as they come down to the ground. So there's a lot of different things that we can use quadratics for. Now this is the first page of your slides, or of your note sheet. A quadratic equation in one variable is an equation that can be written in the standard form of ax squared plus bx plus c, where a, b, and c are real numbers, and a is different than 0. And that's really the reason they include that, is because, well, anything times 0 is 0. So if a is 0, well, we don't have the ax squared term, which really just leaves us with bx plus c, and it would be linear. It wouldn't be a quadratic function. So we can not have a b value or have b 0, that's fine. We have to have an x squared for it still to be a quadratic function. Now you can use various methods to solve quadratic equations. The first one is by graphing the x-intercepts of the rational function, a related function. Well, whenever we're solving, we're trying to find out what value of x makes the function equal 0. Oh, when y is 0 is when it crosses the x-axis. It would be the x-intercepts. So if we can find the x-intercepts, we can find the solutions for the function. And we'll look at the square root method. We've looked at one of those. And by factoring, which we did the last week. Or once we factor it, two things multiply together equals 0, means one of them has to be 0. So when we look at this first one here, we're going to solve it by factoring. Or not factoring, by graphing. Well, if we're going to solve it by graphing, we need to graph the function. Now, normally we would go by taking 5 points, trying to find the vertex as the center point and graph points to either side to see if we can figure out where it would be 0. What we can also do is grab the graphing calculator. And if I want to plug the function in, do y'all remember what we hit first? Well, we turn it on and then hit y equals. Because alpha y equals, that would give us the fraction, yes. Now, if we already have a function in there, we can clear it. And so our function is our x squared minus x minus 6 equals 0 is the one we want to graph, yes? Well, we're trying to find when it is equal to 0, yes? So we don't include that as part of the function because the function is just the x squared minus x minus 6. So I can type in x squared minus x minus 6. So once we get that typed in, go on and hit graph. So again, we're trying to find out where the function equals 0, yes? And the only time it's going to equal 0 when y is 0 is when it crosses the x-axis. So where are the two spots that it crosses the x-axis? So what is the x value at those two spots? Well, this might be hard to tell, yes? So we can try to look at it here, or we can go second graph. Second graph will pull up a table. We need to go up a little bit. So where's the two spots where y is 0? Well, is what value of x gives us 0? Well, one of them is -2 and the other is? X. Yep. So -2 we got, yes? Yeah, so they might not all be contained in the same space. We might have to scroll up and down. Second table, or second graph will give us the table. And then we can kind of scroll up and down to see where the values are. So the solution for this here, where am I at? Right here. We would say that what? X is equal to? And x is equal to? And that's it. Because those are those are the two values that makes this function equal 0. That gives us a y value of 0. And that's it.
Wait, how did you get 3?
So you might have to scroll up and down because it might not include all of them. So if you scroll down.
Oh.
Because it is a quadratic, and we'll see this especially when we hit the next chapter, quadratics will always have two solutions. They might not always be two unique solutions, but we'll always have two. And what I mean by that is we could have that the solution is 3 and 3. We could have the same number, but there is 2. Any other questions on this here? And now there is a way that we can check this, and I've mentioned this to some of y'all, is that we could take these numbers and plug them back in. Because if I take -2 and plug it back into the function, well, -2 squared is +4. Negative and negative give us +2 -6. Well, 4 plus 2 is, and 6 minus 6 is. Because again, when we're solving these, we want to find the value of x that makes the function equal 0. So if we feel like the solution or what we got doesn't seem right, we can always plug it back into the original function that we started with and see, does it give us equal to 0? Well, here it does. So we could do the same thing for +3. Yep. I have the graph written right there. So if we did the same thing for +3, 3 squared minus 3 minus 6. Well, 3 squared is -3 minus 6. And 9 minus 9 would be 0. So we're just plugging them in if we wanted to check them. We could have also plugged them into the calculator. And when plugging them in, go on and put parentheses around the number. Even if there are already parentheses there, putting extra ones in doesn't hurt, especially when we're squaring a negative, because without those parentheses, as we've seen, sometimes gives us the wrong answer. So extra parentheses never hurt. Are we ready for the next one? -x squared, -2x squared minus 2 equals 4x. Well, what are we trying to do? We're wanting to find the value of x that makes this equal 0, yes? Well, what is this equal to? Well, we have two terms on one side and one term on the other, yes? And when we dealt with factoring, we wanted this to equal what? 0. Yes. Because whenever we're dealing with higher degree polynomial functions, when there is a variable with a power greater than 1 in the function that we're trying to solve, we need everything on the same side. So the first thing I would do is subtract 4x from both sides, which will tell us negative 2x squared minus 4x minus 2 is equal to 0. Now at this point here, when we were solving it, we would divide, or factoring, we divided everything by negative 1 to make the term in front of x squared positive, because we didn't want to deal with a negative in front of the x squared. Well, if we're graphing this, does the calculator really care that we have a negative 2 in front of x squared? No. So we can leave it exactly as this. Here, we just need everything on one side. So when we go back to y equals, we can clear this out and go negative 2x squared minus 4x minus 2. We typed it in and hit graph. So how many times does it cross the graph, or cross the x-axis? Does it cross the x-axis? No. It comes up and touches the x-axis and then goes back down, yes? If we go second graph, so looking at the table, well, I do have at negative 1, 0. When x is negative 1, the y value is 0, yes? Well, the one below it tells me 0, negative 2. Is that one of our values? No, because we're wanting to what? We want to know the values of x that will make the y be 0. What values of x will make this function equal 0? So negative 1 is our solution. Does anybody have a guess at what the other one would be? Negative 1. It still has two solutions, but the solutions are x equals negative 1 and x equals negative 1. This here is one of the cases where we don't have two unique solutions, but we still have two. What they consider this to be is an even degree. This solution is an even degree, or sorry, not even degree, even multiplicity. Anytime a function touches the x-axis but does not cross it, it's considered to have an even multiplicity. So the number of zeros that appear at that spot is going to be an even number. So for here, since it's a quadratic, we only have 2. The number that appear there are 2. But it could be 4, 6, 8, multiples. But there are 2 there. So when we're asked about the solution, well, we can say x is equal to negative 1. We don't have to list it twice unless it asks for both. It's saying list both solutions. It's just x equals negative 1. We can list it twice. That's not wrong. It's just x equals negative 1. We ready for the next one? There's that graph. X squared minus 8x plus 12. Well, it is equal to 0 already, yes? That means I can go over to my graphing calculator and hit y equals. And we can type the function in. X squared minus 8x plus 12. And once we get done with that, we hit graph. And where are zeros at? Because it looks like 2 and 6. And if we wanted to make sure, we can go second graph. And we see that at 2, the y value is 0, and at 6, the y value is at 0. So that means for us, the solution for here is x equals 2 and 6. I will take this version also. And a lot of books and a lot of mathematicians will put the answer like this here, x equals 2 comma 6, instead of rewriting out x equals twice. Any questions on any of this here? We good with this here? Do we need to see another example of one of these here? Yep. Reset that. Let's look at this one here. I want to look at this one here, and then we'll move on. 1/2 x squared equals 6x minus 20. Now, when we were factoring or doing those kind of operations, we would want to try to keep the x squared positive. But since we're graphing it here, it really doesn't matter. Let's go on and move the 1/2 over. 1/2 x squared. By subtracting it from both sides. And what that would give us is 0 equals negative 1/2 x squared plus 6x minus 20, because we just moved it over. And since we do have it equal to 0, we can go on and plug it into the calculator. So we good to move on to the graphing? Okay. So I'd hit y equals, and I'd clear that out. Now to get the fraction, we can go alpha y equals, enter. We can say negative 1/2 x squared plus 6x minus 20. And I have a feeling that there's something wrong with this graph. Did everybody get it typed in? Because you could put negative 6x, but the x squared and the 20 would both have to be positive. We get something like this here, yes? Now, if we would left it positive, 1 alpha y equals, enter 2 x squared minus, well, I get the minus, 6x plus 20. Because if we factor that negative out, it would have really just changed the signs. And the other one would look like this here. Because it's really that negative 1 is going to be a reflection across the x-axis. So where does it cross the x-axis? It doesn't, right? So if it doesn't cross the x-axis, that means what? Exactly. So it is no real there is no real solution. It's not that there is no solution, it's no real solution. Well, if something's not real, it would be what? Fake or imaginary. So by the end of this chapter, we will find the solutions for this function. There are solutions, they are just not real solutions. So if it's just asking to solve the equation or to find the real solutions, well, this one doesn't have real solutions. If it's asking us to find all of these solutions, well, we can't use graphing. because it won't tell us what they are. Because graphing only works if it crosses the x-axis at whole numbers. Because I have a feeling if we did this one here, clear both of those out, 4x squared minus 12x plus 9, and we graph this here. Well, that's between 1 and 2, yes? Well, do we know exactly what it is? No. Now, there's ways we can go about finding it and seeing if it works out. It could also be that it barely crosses. So there are 2 points right there, but they're ugly decimals. So this here, graphing works well if we have nice whole number solutions. Then it will give us the answers. Any questions on this here? It will actually have solutions to it. It actually works out the solution is 1.5. So it's a fraction, and we would have to use calculations or change the scale to go by halves to see if that works. But a lot of the times, especially, well, if you're doing the assignments and you have ample time to mess with the scales of the x-axis to get there, that works out fine. But on the ACT, where it just gives you the function, find the real zeros or find the zeros of the function, when we get to the quadratic function, the last one that we'll cover, it's sometimes easier to just type it in there than it is to try to mess with the scale and seeing if we get that. Because it could be by halves, or it could be by quarters, or thirds, or eighths, or there's any number of ways we can look at it. But a lot of the times, if it's asking for real solutions for the quadratic function, the ACT will give you answer choices, yes? So what could we do with those answer choices? We could plug them in and see which one gives us 0. If a value does give us 0, that works, and any of the answer choices that doesn't have it are gone. Now, we'll probably end up finishing out today with these here, and then do a few more tomorrow, and I will give you the rest of the time tomorrow to work on the assignment. But what we're looking at here is we want to solve each equation using the square root method. Now, the reason or way that the square root method works is in one of two cases. If we have x squared, but no other variables, so we don't have x to the first, our middle term, we can use the square root method. The other way is if I'm given an equation with a set of parentheses squared already, where there's no other variables outside of those parentheses squared, then we can use this. And given this method, really what we're doing is we're either getting the term that's squared by itself or the set of parentheses that is squared by itself first, and everything else on the other side. So if I look at this, 4x squared minus 31 equals 49. I want to get everything away from the x squared. Well, what I can do is add 31 to both sides. So this is negative 31 plus 31 is 0, leaving me with 4x squared equals. Is the x squared by itself? Divide both sides by 4. So any questions on how we got x squared by itself? Okay. Well, now we need to reduce the power somehow. Yes, it's called the what? Square root method. So we'll square root both sides. Plus or minus, because the square root of 20, we're looking for what number times itself is 20. Now the graphing calculator will give you a decimal number, 4 point. Yeah. Now, if you use the yellow calculator, the TI-30XS, the yellow or white calculators, and take the square root of 20, it'll actually tell you that it's 2 square root of 5. Because if we look at 20, well, 20 is 4 times 5. The square root of 4 is 2, so it comes out. But we can't take the square root of 5, so it stays. Now, we need the plus or minus, because a negative times a negative is a. So negative 2 square root of 5 times negative 2 square root of 5 would be positive 20. And the positive 2 square root of 5 times positive 2 square root of 5 would also give us positive 20. So we have both cases. So whenever we take the square root of both sides, we're going to need the plus and minus. Now, if we square both sides, we don't need it. It's only when we square root. Because when we square root both sides, we're saying that we're taking a number that is squared, that could be positive or negative for x, that ends up being a positive number. We need both. But when we're squaring both sides, it can't be both. It's going to be probably one or the other. But that's all we have to do for this here. Questions on this? Now, will this method work for every single quadratic we come across? Because what did we start out with? If we have a set of parentheses that's squared and no variable anywhere else, or we have x squared and there's no other variable, then this works. But if it's not, if we actually have it in standard form, ax squared plus bx plus c, we have a bx term, then we can't use this method. Well, we can. It's more work to do it, because we'd have to get it as a single set of parentheses squared, then apply the square root. Here, 3x squared minus 9 equals 0. But we do have just an x squared term. So we want to get the x squared by itself. And we can do that by doing what first? We can add 9 to both sides. Because when we add 9 to both sides, we'll get that 3x squared equals 9. What can we do next? Which tells us that x squared is equal to 3. Any questions on how we got to the fact that x squared equals 3? What would we do next? Square root both sides. Now the square root of x squared is equals plus or minus. Are there two numbers that multiply together to give me 3? Is 3 prime? 1 and 3, yes? So that's going to be the square root of 3. Anytime we have a prime number we're trying to take the square root of, it's just going to be the square root of whatever that number is. Because by definition, a number is prime if its only factors are 1 and its self. That's the only way that it's prime. Does anybody know what the smallest prime number is? It is not 1. 2, because 2 is 1 times 2, yes? And 1 times 1 is still 1, times 1 is still, so we can't really write it as a number times itself because it would be indefinite. And it also messes with the prime factorization, because prime factorization is just the smallest we can break a number up. And if 1 is prime, we can continue to add it infinitely, so we would never actually get it. It's a small unknown fact that 1's not prime, even though it was officially declared not prime in like the 1700s. So